Hey Internet, welcome back to the Aimless Electron. In this video I'd like to describe a screen that we created for Burning Man 2015. And this screen was made out of long strips of those ws2812 LEDs. I'll tell you a little bit about how we created the hardware, which is a little over complex for that one, and then the idea for the new hardware in 2016. As an intermediate step, we actually built another controller for just one of the panels, which turns out to be about 4 foot wide by about 3 foot tall. This one was for a relay race called Ragnar. Ragnar is this crazy race. I'll post some information about it at the bottom, but it's a 200-mile running race from Huntington Beach, California to San Diego with a team of 12 people in 2 vans. We decided that we wanted to decorate one of the vans with this screen, so we taped it to the side of it. Really awesome. I'll post in the videos of it and some pictures of it later on. For now, let's go over how these ws2812s work, and then the hardware that was used in 2015, the hardware that we'd like to use in 2016, and how we put together this intermediate step. Also, I'll take a quick look at some of the code that we used, but I'm not going to go into that too deep. I'm actually going to work on another channel that is more concentrated on code, and I'll link that in eventually at the bottom as well. For now, let's go check out that hardware. So let's talk for a second about how these ws2812 chips work. They're actually 3 LEDs in one, and they have a small microprocessor in them as well. So we'll draw a little microprocessor here. And one for each color. It actually starts off with red in the middle, blue at the end, and it starts off with green for the first color. What this little chip does is just PWM these, so you get different brightnesses out depending on what signal you get in. Now there's a data inline. It's just serial. Then it sends the data out. These little chips also have a +5 and a ground on them. So just little 4-pin chips that are surface mount. The way it shifts in data is it expects 24 bits. In other words, 3 bytes, 1 for each color. It shifts it in until it's full, and then any other data it gets after that, it shifts out to the next one. Well, where's the clock, right? How do you deal with the clock? The way that's set up is it's expecting a bit to come in a certain time frame, and expecting a certain pulse length for a 0 or a 1. In other words, it expects a bit every 1.25 microseconds, and it expects the pulse to look like this for 0, and this for 1. And in case you can't see that really clearly, that's about 1/3 of the time on and 2/3 off for 0, 2/3 of the time on and 1/3 off for a 1, where these short pulses, both here and both here, are around 4 to 4.5, or sorry, 4.45 microseconds, or 0.45 microseconds over here. The longer pulses are around 0.8. Well, the nice thing about this is that 1.25 microseconds can actually vary by plus or minus 0.300 microseconds, or 300 nanoseconds. So that means you can actually go down to 1 microsecond per bit, which will give you approximately 1 megahertz frequency to send through these. There are a couple other things. If it's idle for approximately 50 microseconds, that means the line is low for 50 microseconds, these will reset. Now they won't change color, they will just reset and know that no other data going through them is going to be used. That also means that if you've got a bit way down the line and you've got too many of these lit up, you're going to start losing information. Certain ones in the front will get their information, then they'll wait for everything else to go through for 50 microseconds, and all of a sudden they'll switch back. There's nothing you can really do about that. So if you have a big screen like we do, you have to break it up into chunks. You fill out one chunk, let it sit there, fill out another chunk, and let it sit there. So next, let's talk about how we set up the old setup for Burning Man 2015. For Burning Man 2015, we actually wanted to have 4 panels, the same size as what I was telling you about earlier. These were 4 foot by 3 foot, and they were 75 pixels, or 75 LEDs, by 48 LEDs. So a total of 3,600 LEDs per panel. We were originally going to have 4 of them. We ended up only doing 3, but we did build the hardware, or at least the electronics. I built the electronics to handle 4 panels. Well, 4 panels equals a total of 100 or 14,400 pixels total. Well, let's do a little bit of math. We wanted to do 20 frames per second. So how much data did we need to push through at the bare minimum to draw these 14,400 pixels at 20 frames per second? Well, first of all, we had to take 14,400, multiply it by 3. When you do that, you get somewhere around 43,200. Well, why times 3? Well, there's 3 colors. It's 24 bits, so 1 byte per color. That's how much data we need to draw for these screens. Then we have to multiply that by 20. Well, after we multiply that by 20, we're way up there. 864,000 bytes per second. Even at a relatively modest 8 bits per byte serial with a start bit and a stop bit, 10 bits on serial. So if we want to do serial, we'd have to do at least 8.64 meg baud rate. That's way faster than most normal RS-232s can handle. So what are we going to do here? What am I going to do here? Well, turns out that if I use one of the X-Mega chips from Atmel, and the X-Mega 12812b, well, this has built-in USB, and that USB can support those speeds, and it doesn't have to quite go as fast. We can go down to about 8 megahertz on the bus speed for that. It's not as bad. So using this 128.8.4u is great, but how do we draw 4 screens? How do we draw a total of 300 pixels across and 48 pixels down? It's way too much to fit in the memory for this thing, and we can't draw it just line by line. We have to draw this in segments because it's too slow to set those pixels. Remember, we're only doing about 1 megahertz out on those pixels. And that's per bit, not per byte. Well, what did I do? I decided I'll use a whole bunch of chips and I'll use their memory to draw sections of each panel, and each panel was then divided up into 6 rows. So 1, 2, 3, 4. And these 6 rows just basically wrapped around like this. They were connected so it snaked around. Now all I did was divide the 48 by 6, so we had 8 lines in each one of these rows. And 8 times 75, well, if you do the math, it's within that 1,000 range, right? It's only 600 pixels per each section. So that I can draw, and 600 times 3 is only 1,800. That's only 1.8 kilobits, or kilobytes, and these little X Megas have 8K of memory, so that's plenty to fit in there. So how does that all fit together? Well, the idea is each one of these lines was connected to an X Mega, and that's a lot of X Megas. 4 panels times 6 lines, we had 24 of these little X Megas. Way overkill, not using the processing power efficiently, just kind of using it for the memory, really. The configuration on top of that. What happened, we have one X Mega with the USB connection coming in. It has this data bus that comes out, just an 8-bit data bus. And it also has a connection to a couple 4 to 16 line decoders. I'm just going to draw this like this. So there's all these 4 to 16 line decoders coming up. Then one more pin on the enable on each one of them. This is actually used as the clock. Well, the clock for what? Well, on each of those 24 other X megas, we connect this 8-bit bus. I'm only going to draw a couple of them right here. Then we have a clock out for each one of them from these 4 to 16 line decoders. As we'd step through which line was activated on the 4 to 16 line decoder, that clock would be activated on just that single line, which means whatever data was coming out of this 8-bit bus would be fed to one specific chip. That chip would in turn store whatever it received inside of its memory, inside the RAM on the X mega. Finally, there was another sync line, and this sync line was attached to every single one of the 24 X megas. When we were done feeding out all the information for an entire screen, all 4 panels, we would flip this high for a microsecond or so, and that was the indication to these chips to push out the data serially to the screen. So all 24 chips would draw their little section of 600 pixels at once. And that's how all these screens were drawn. Well, that in theory works great beyond the fact that we're really wasting a lot of power in these. And it could have worked. I could have used a smaller X Mega or even a cheaper AT Tiny perhaps with just enough memory inside of it. It's just I had the layout for these. I knew how to program these and I was running really short on time. So I took the cost of what it took to make these over the time. That being said, I didn't have the time to fully work out all the electronics that were necessary, all the filtering for the power, and one of the biggest problems is these were 5 volts and these are 3.3, which means these lines here were also 3.3. What's wrong with that? Well, it didn't quite drive these pixels enough. These pixels turning on and off caused a lot of noise to be put on the power rails. And that noise combined with a lower than optimal signal voltage meant that sometimes these didn't show up right. And I didn't really work with that. I want to show you the hardware itself, just to give you an idea of what we did. Right here is the main controller board. USB came in here. I tried to do a little bit of filtering on the power. Obviously there were a couple of mistakes. Again, very last minute stuff. In fact, some of the traces weren't even done correctly. And it was really hard to tell sometimes if a connection made it to a pad. It looked like it did until you zoomed way in. Anyways, here's the main chip where the data came in, the 2 4 to 16 line decoders, and then all the clock signals out. I don't know if you can see those traces or not, but that's where they came out right there. Then I had a couple of these ribbon connectors that went off to 2 different boards, each with 12 of the X megas that drove the screen. Those boards look like this. These are just the programming headers so I could program them after they were on board, just little PDI. This is where the signal came in. This is where the serial for the screen came out. Right here, as you can see, here's all the chips. If you look really closely, a bunch of these had to be jumpered. Again, that was because the software made it really difficult to tell if they were connected. And the nets worked okay. Sometimes it caught it, sometimes it didn't. Maybe this was my own fault. Maybe this was me trying to work through it too quickly at wee hours of the night and still go to work. That being said, it needs to be redone. So what's the idea for the new one? Well, instead of all those chips, all those 8-bit chips, and trust me, I like to squeeze as much power out of that little chip as possible, whatever I can get out of it. It just kind of doesn't become worth it. Not to mention, since it's USB, I have to connect something to a computer that acts as a USB host, and the drivers have to be there and everything like that for the USB. So instead, why not just use one of those little cheap Wi-Fi modules? They're like $3 maybe, and they're high speed. You can get, I believe, up to 80 megahertz on the SPI bus, though I don't think it'll work real well and not much supports that. I know it'll work at least 40 according to a lot of what I read. So you just got this little Wi-Fi chip connected via SPI to your microcontroller. Well, this time instead of using the little 8-bit microcontroller, I'm going to use one of the SAMs from Atmel. And this is an ARM-based processor. Not only is it running at 300 megahertz, but it has a ton of I/O. There's, in this package, like 96 I/Os that you can use. And that means instead of having to have some weird format where it loops around like this, and I have to put in special bits, I can actually, if I wanted to, connect 48 lines directly. I can connect all 48 lines directly to the chip. That is a bit of waste on the wiring, but if you have it connected upright, it'll work just fine. You do have to solder it on at some point, right? You either have to solder a wire on this end or on that end. The difference is, this again being 3.3 volts, is there needs to be a level shifter in here. And this will do the 3.3 to 5 volt conversion. And it'll also act as a buffer, so if there's any feedback on these lines from all the weird power going on here, or if something shorts, it's going to hit this, which is a lot better protected than this, and it's not going to blow up the chip. Pretty simple. Problem is, I don't know how to program these SAM arms yet, and I'm working on that, and I'll figure it out. So in the meantime, we had the Ragnar race, and we wanted to do one of these screens. So I sat down and I reevaluated the hardware and the requirements and said, okay, you know what, well, let's not worry about doing 20 frames per second. Let's see if we can do at least 5. And I actually got this thing to do between 6 to 7 frames per second. So it wasn't bad, but it was just one screen. We were just going to put one of these screens instead of 4 of them on the van. So this time we only had to deal with 3,600 chips, and it's still a pretty big number. And that still means times 3, we cannot fit that in the RAM because we're looking at 108K, and we're limited to 8K. So that wasn't going to work. Besides, we still have a problem of it being pretty slow. Now I guarantee you there's ways that we could have done like half the screen and started the screen drawing while the other half the screen was loading up in serial. Another one of those situations where I ran out of time. It was just too close to the end to do something like that. So here's what we did with the hardware. We just did one of the FTDI chips to go from USB to UART. And then from UART over to one of the regular X Megas. In fact, the X Mega I used off of here was off of another board that I desoldered these all. Surprisingly enough, they still worked. I didn't destroy them by overheating them, or shorting them out, or shocking them with the ESD. Lucky me. So after this X Mega, we did send it again to one of the 4 to 16 line decoders, but this time we used the actual data out on the enable pin. So the data that was going to the screen was sent out here. Then one of the 4 to 16 lines went to the buffer we were talking about before, the buffer that converted the 3.3 volts to 5 volts. This worked beautifully. Decided just to do 16 and split up the panel into a total of 16 3-line segments where we just had the line wrap around twice. So this went off to all 16. There were actually 2 of these, and I'm sorry, 1 of these and 2 of these, because these only do 8, so we had 8 and 8. And then these came out to the screen. The reason that we shifted this down is so we could draw this, let it sit there, and not try to push data all the way down and have the bytes look weird. It still took about 100 to 125 milliseconds to draw the entire screen, which isn't super fast, but it did mean it was smooth enough to look like somebody was drawing a picture once. And you could kind of show video. We showed some animation from YouTube that was captured on a laptop. Now let's talk for just a second about the internals. I'm not going to go over code itself. I'm just going to tell you how I set up the processor. There are 2 main parts to this setup. The first one is, instead of putting together code which actually turned on a port, just a pin I guess, for a high and low sequence depending on if it was a 0 or 1, and waiting during that, I used another SPI. I set the SPI's clock frequency to about 8 megahertz. And then if the bit was 1, I actually set the SPI's data port to something like this. And if it was a 0, I set the SPI's data port to something like this. So in other words, when the data was coming out, we had this long pulse and then a short pulse. If it was 1. If it was a 0, we had a short pulse and then a long pulse. The point here is this clocking out of data was handled by the SPI port. So while that was doing its clocking out of data, we were free to do something else. This was a completely separate process. We could receive more data in from the RS-232 or the UART. We could increment some variables to keep track of our row and column count and our bit shifting. All that stuff could happen while this SPI was working. Saved us a lot of time, let us pump through the data. The next thing that's important here is the modes. Consider for a second that you want to push through about 12 bytes of data. So you have 12 bytes that you want to bring into through your serial port. Well, how do you know when you're done sending that 12, or how do you know if you stopped partway through? How do you know that you've only sent through, say, 8 bytes and it's just sitting there? Well, we used a timer. We used a timer that said, okay, it's never going to take more than 1 millisecond to send in 12 bytes. And if that 1 millisecond timer elapses, that means that we've got a fault condition and we will reset this buffer. We'll reset whatever that's going into. So you've got this all going into a buffer, and if the timer elapses, then reset the buffer. However, if we get all 12 bytes, we reset the timer. So we have all bytes received, then we reset the timer and wait for the next set of bytes. That took care of one problem. That made sure that if we were streaming data in or whatever data was coming in, the processor wasn't stuck, as long as we made sure that our computer could push the data in quick enough. Just to finish this off, I'll tell you that we had a couple of modes for our serial communication. We had a command, and after the command, depending on the command, we could either have data, which was just a couple bytes, or we could stream. The streaming mode is what we use to push data through to the screen. As the data was coming in, it was automatically being clocked out to the screen, and that way we didn't have to worry about memory storage. What that did mean is we were maxed out to about 8,500 baud, or 85,000 baud. We couldn't get up in the megahertz range because we'd be trying to push data too fast to the processor and we'd lose bits. Bits wouldn't be able to make it out. So in just a minute, I'll show you that hardware. So starting with the prototype board, going over what we did, what I drew out. Here's a little FTDI, right? And the USB just plugs in here. The nice thing about this FTDI is it actually can supply power to this as well. It has a little header here that allows you to select 3.3 or 5 volts. Well, if you plug something into this pin, you also get 5 volts. So you can get both your 3.3 volt logic and your 5 volt logic that you need. So you can do the level shifting. The setup of this. The serial connection comes in to the chip. The chip does what it needs to do with it. Shifts through these 4 lines to this 4 to 16 line decoder. This is the actual data out, which is just connected to the enable pin of the 4 to 16 line decoder. That means whatever line is selected is going to turn on and off at the same rate that this is turning on and off, and it's plenty fast to handle a 1 megahertz signal. 1 megahertz again being how fast we can clock bits through our LEDs. From there, each of these 16 lines out, the other 8 are up here, where the bottom 8 are right here, go through one of these buffers. It's just a simple octal buffer, except it can accept 3.3 in and is connected, even though I don't have it connected right now, to the 5 volts supplied by this. So it's getting 5 volts out, and then on this side, that goes to our screen. So let's look at the actual prototyped hardware. This was the final design. This is what we actually connected to. Here's our little FTDI board, a little right angle header, a jumper that supplied our 5 volt, and this little jumper right here set to 3.3 volts. So we've got our 3.3 volt in and our 5 volt in, and then just a ground. This wire connected to the ground for the power for the actual LEDs, which was separate from what this was, so we could supply enough current and it wouldn't necessarily interfere directly. This was some extra filtering that was going to be used just in case, but was left dangling, so it's really just kind of sitting on the board. Here's our 4 to 16 line decoder and the 2 buffers coming out. It just so happened that since I had a couple extra RJ45 connectors, I just attached them on there. 8 lines on a network cable, so 8 and 8, 16. I had actually created the panels for the screen in 2 separate panels, so that made it nice. They were modular. One half of the panel connected to one half of the panel connected to the other. Before I go, I wanted to show you what I used for the power. It was just this cheap little eBay find that converts 12 volts to 5 volts. Now, sitting alone with no powered cooling, no air blowing across it, it'll handle about 150 watts, which was perfect for one screen. If we got some power blowing across it, it'll handle 250 watts, but heck, didn't need any of that. It just sat on the floor, on the rubberized floor, thank God, so this didn't short out, and supplied power just as needed to the screen. The screen handled it just fine. I'd like to show you how I constructed the screen real quick as well before I go on to the videos. So right after that, I'll show you the videos of the screen working, or at least one of them, and a couple pictures. Okay, the screens are a bit too big to just hold the camera over on the stand above my desk, as you can see. This is half of a screen. There's only 24 pixels going up, but all 75 going across. The backing is just a piece of plexiglass, very thin plexiglass. There's the data in, those green wires right there, all 8 of them, and then the power connections. And they just go off to the edge right there. The nice thing about this design is it also can fold up in the center, just split it. Makes a nice compact screen because both of them do that and can just stack on top of each other.
Thank you to everybody who helped out, all of my friends who put in the countless hours, everybody at Shoot Bay. It may not be perfect, but it's fucking awesome. Oh shit, I can't believe it worked. And this is working better than it did at Burning Man too, so that's awesome.
Well, that was a long video, so if you're still watching, thanks. And I'd also like to say thanks to my friends who helped me create those screens and to my girlfriend for being patient while we did all that work. And if you like this video, stick around because this will probably be just part 1 in a multi-part video on making driver hardware for those screens and writing some software. Again, if you liked it, give it a thumbs up, subscribe to the channel, and leave me some comments. Let me know what you thought about the video, maybe what we could do better, or something you'd like me to record for you. So I'll see you in the next one.